Hello, I'm Valerie Maッソン Delmotte, climate scientist and co-chair of the IPCC working group on the physical science basis on climate change. Thank you for this opportunity to share with you key findings from our latest climate report. This report reflects major advances from multiple lines of scientific evidence, observations, insights from past climates, improved understanding of drivers, processes and feedbacks, and insights from global and regional climate modeling. We designed this report to bring these multiple lines of evidence together regarding climate change at the global scale, what is observed, the causes of changes, what to expect in the future, regarding our understanding of the mechanisms shaping the global and regional climate, the energy, carbon, and water global cycles, the ocean cryosphere and sea level, and the interplay between human influence on climate and air quality. And around a third of this report is focused on regional climate information, with an emphasis on methods, extreme events, and information relevant for risk management and adaptation at regional scales. We can thus provide today the clearest picture of how the Earth's climate functions and how human activities affect it. We know better than ever how the climate has changed in the past, why, how it is changing now, and how it can change in the future. I would like to acknowledge the major contributions from Japan to this report through the role of Japan's scientists for climate science advances, through the dedication of the Japanese scientists who have accepted to be volunteer lead authors, contributors, and reviewers of the report, and through the constant support of the Japanese government to the work of the IPCC, including during the two-week approval session last summer. Building on the summary for policymakers, which has been approved by delegates from all governments, let's look at the key findings. Where are we now? Recent changes in the climate are widespread, from the high mountains and the high atmosphere to the top of the ocean, from the poles to the tropics. They are rapid, intensifying, and unprecedented over thousands of years or more. The level of CO2 in the atmosphere is now unprecedented compared to the past 2 million years. Sea level is rising at an accelerated pace, and this is unprecedented in several thousands of years. Let's focus on one of the key indicators of the state of the climate, changes in surface temperature at the Earth's surface compared to the average over the late 19th century. Today, the observed warming is reaching 1.1 degrees Celsius, averaged over the last decade. Our best estimate is that all of this observed warming is due to human influence, driven by the warming effect of our past and current emissions of greenhouse gases, primarily carbon dioxide and methane, partly masked by the cooling effect of pollution particles. Human-induced climate change is already affecting every region on Earth in multiple ways, strengthening the frequency and intensity of extreme events such as heat waves, heavy precipitation events, droughts, and fire weather. The global proportion of major tropical cyclones categories 3 to 5 occurrence has increased over the last 4 decades, and the latitude where tropical cyclones in the western North Pacific reach their peak intensity has shifted northward. Human-induced climate change increases heavy precipitation associated with such tropical cyclones. Multiple changes are taking place in the ocean: more heat waves, acidification due to the uptake of carbon dioxide, loss of oxygen due to less mixing in the surface. Unless there are immediate, rapid and large-scale reductions in greenhouse gas emissions, it will be impossible to limit warming close to 1.5 degrees Celsius or well below 2 degrees, the goals of the Paris Agreement. What are our possible climate futures? First of all, it is critical to understand that the changes that are experienced everywhere in Japan and every region will increase with further warming. Based on a set of scenarios that span a broad range of possible future human influence, scenarios in blue with a large decrease or a very large decrease in greenhouse gas emissions, a scenario where these emissions stagnate over the next decades, and scenarios with the assumption that human greenhouse gas emissions will continue to increase fast or very fast during this century. From all this broad set of possible emission scenarios, you can see that global surface temperature will continue to increase at least until the mid-century. If greenhouse gas emissions stagnate close to today's level, global warming would exceed 1.5 degrees Celsius, averaged over 20 years, in the next 20 years, 2 degrees by 2050, and 3 degrees in the next century. This can be avoided if deep reductions in carbon dioxide and other greenhouse gas emissions occur as soon as possible and continue year after year in the coming decades. Many changes in the climate system are directly related to the level of global warming. These include regional trends in temperature, the upper panel here, and precipitation. With every further increment of global warming, regional trends in temperature and contrasted trends in precipitation will continue to increase. This is also the case for the frequency and intensity of hot extremes, marine heat waves that are so damaging for marine life, heavy precipitation, droughts in some regions, especially soil droughts, which affects agriculture and ecosystems, and the proportion of intense tropical cyclones. It's also the case for the reductions in snow cover in mountains, permafrost thaw, and the loss of Arctic sea ice. It means that we need to be prepared for extreme events with a larger magnitude and increased frequency, affecting new locations or occurring at different times compared to today, or rare new combinations of events that are associated with a lower probability of occurrence, but potentially much larger effect. A warmer climate will also intensify the water cycle and its variability, including very wet and very dry weather and climate events and seasons, with implications for flooding, drought, and more broadly, water management. Reduced ocean mixing, increased ocean acidification, and loss of ice will continue to increase in the 21st century, but at slower rates if greenhouse gas emissions decrease. This is very important for protecting marine life and people who depend on it. However, many changes due to past and future greenhouse gas emissions are irreversible for thousands of years. It is the case for the warming to date due to the ocean heat uptake. It is the case for the deep perturbation of the global carbon cycle, including deep ocean acidification. And it is also the case for the increase in the heat content of the deep ocean, the melt of ice sheets, melt of Greenland, faster flow in several sectors of Antarctica. As a result, sea level rise will continue in the coming centuries to millennia, and it's critical to be informed by the best available knowledge for coastal risk management and coastal planning. The projections of global temperature in this report are improved through progress in assessing climate feedbacks and climate sensitivity. The range associated with the warming responses shown before is much lower, much smaller than previously. And we have also provided sea level projections that are fully consistent with our understanding of climate feedbacks and the global temperature response. This is reported here. It is certain that sea level rise will continue. You can see that by 2050, it's mostly independent of the emission scenario. There's a spread by a factor of almost 2 by the end of the century, in between scenarios with very low or very high greenhouse gas emissions. Following requests from those who manage critical infrastructure on the coast, we also report what would be the added contribution from poorly understood ice sheet instability processes that could lead to low likelihood, high impact eventualities in the case of the occurrence of ice sheet instability processes. Over several hundreds to thousands of years, multi-meter sea level rise would happen. However, you can see that by the end of the century and later on, the rate, the scale of sea level rise strongly depends on the emission scenarios and on our ability to limit the level of global warming at the lowest possible levels. Our report provides a wealth of knowledge in terms of climate information for risk assessment and regional adaptation for Japan and all world regions. With further warming, every region is projected to increasingly experience concurrent and multiple changes in what we call climatic impact drivers, which are physical changes in the climate system, such as trends, extremes, values above known tolerance thresholds, which we know are associated with impacts, physical impacts, impacts on ecosystems and societies in various sectors. These changes will be more widespread and pronounced with every additional fraction of global warming. As I stressed, low likelihood outcomes such as ice sheet collapse, abrupt ocean circulation changes, or rare compound extreme events cannot be ruled out, and they are part of risk assessment. The probability of such outcomes increases with higher global warming levels. So, from a physical science perspective, what is needed to limit future climate change? This report confirms that every ton of CO2 emissions add to global warming. There's a near linear relationship due to compensating effects between nonlinear processes in between the level of warming and cumulative past, present, and future CO2 emissions. As a result, limiting human-induced warming to any specific level requires limiting cumulative CO2 emissions, and warming will stop due to CO2 when we reach, from human activities, net zero CO2 emissions. It is also required to limit warming, to limit the emissions of other greenhouse gases. We stress that strong, rapid, and sustained reductions in methane emissions would also limit the warming effect resulting from declining aerosol pollution and would thus improve air quality because emissions of methane are a precursor of the formation of ozone near the surface, which is an atmospheric pollutant, harmful for our health and for terrestrial ecosystems. The good news are that reduced global greenhouse gas emissions year after year will lead within years to discernible effects on greenhouse gas and aerosol concentrations in the atmosphere, therefore quickly improved air quality, which is important for health, compared to scenarios with high global greenhouse gas emissions. The effects for trends in global surface temperature would be seen within around 20 years. As you can see, while there is no going back for some changes in the climate system, they can be slowed, and other changes which directly depend on the level of warming can be stopped by limiting warming. The climate we experience in the future depends on our decisions now. What do I expect from this online symposium? I expect participants to have a clearer understanding of the links between their greenhouse gas emissions, the resulting level of global warming due to the imbalance of the Earth's energy budget, and the direct consequences for regional climate in Japan and around the world, and the long-lasting consequences for sea level rise and their implications for sustainable development. I expect this symposium to motivate climate action in Japan, acting both on the cause of climate change to quickly reduce emissions of greenhouse gases, mostly driven by the use of coal, gas, and fossil fuels, but also those associated with land use changes and the food system, as well as acting on the consequences of climate change. This report provides a wealth of information on future changes, and especially knowledge related to unprecedented extreme weather and climate events, with larger magnitudes, frequencies affecting new locations, occurring at different timings or new combinations. It provides information on low likelihood, but also potentially high impact eventualities, so as to include them in risk management to design climate resilient development. This scientific knowledge needs to be used to inform today's choices so as to prepare for these changes, build on the latest scientific knowledge, to limit the scale of the associated risks through risk management and adaptation strategies. For instance, you can use our interactive atlas, which is a new dimension of IPCC reports using open science, open data approaches to allow you to make interactively visual representations or to download the data. You can also use our regional fact sheets, 2-page summaries of the major findings from this report at the scale of large world regions. I also expect this report to be used to develop resources for education, teaching, and training. Finally, how can early career scientists contribute to IPCC reports? I have flagged robust findings from our report, but it also shows current knowledge gaps and remaining core uncertainties, and therefore it can be used to identify stringent research priorities. Young scientists can contribute by developing and publishing cutting-edge new knowledge, or through in-depth reviews of the state of knowledge. For instance, a recent review of the current understanding of climate sensitivity, bringing together all available lines of evidence, played a key role in our assessment, with reducing the spread of global surface temperature response to emission scenarios a major advance. Young scientists can play a key role as reviewers of successive drafts of the report. This review process is critical for the rigor, the exhaustivity, the robustness of the assessment. In this report, there have been major contributions by early career scientists as individuals, but also through coordinated group reviews, for instance, through international associations of early career scientists in geosciences or in polar sciences. Young scientists have been also involved as chapter scientists, supporting chapter teams for multiple aspects, and sometimes playing a key role in some of the report tools, such as emulators, simplified climate models, or the report datasets, or novel developments, such as our interactive online atlas. As you can see, we have done our best to enhance an open science, open data approach in the report, to make information and tools supporting the assessment, data, code openly available to everyone, following the best practices for scientific data management and stewardship. And this is a resource for early career scientists to further develop science advances. And finally, we are currently planning a collective effort to consider carefully what could be and what could not be assessed in this report, and what are the insights for future research needs and for international climate science coordination. This will be a joint effort between the IPCC Working Group 1 and the World Climate Research Programme. We intend to run open consultations in the first months of 2022, followed by hybrid meetings. I would like to invite Japanese scientists, and especially early career scientists, to contribute to this brainstorming. Thank you very much for your attention, and I wish you a fruitful symposium. Goodbye.